Hello everyone. Today the topic which we are going to see is convolutional neural network CNN. CNN is a class of deep neural networks most commonly applied to analyze visual images. The name convolutional neural network indicates that the network employs a mathematical operation called convolution. Convolution is a specialized kind of linear operation. Convolutional networks are simple neural network that uses convolution in place of general matrix multiplication in at least one of their layers. What are convolutional neural networks? A convolutional neural network CNN is a specific type of artificial neural network that uses perceptrons, a machine learning unit algorithm for a supervised learning to analyze data. CNNs apply to image processing, natural language processing, and other kinds of cognitive tasks. A convolutional neural network is also known as convoluent. CNNs are a regularized version of multilayer perceptron. Multilayer perceptrons usually refer to fully connected network. That is, each neuron in one layer is connected to all the neurons in the next layer. The fully connectedness of this network makes them prone to overfitting data. Typical ways of regularization include adding some form of magnitude measurement of weights to the loss function. However, CNNs take a different approach towards regularization. They take advantage of the hierarchical pattern in data and assemble more complex patterns using smaller and simpler patterns. Therefore, on the scale of connectedness and complexity, CNNs are on the lower extreme. They are also known as shift invariant or space invariant artificial neural networks, based on the shared weights architecture and translation invariance characteristics. What do you see when you look at this image? Do you see a person looking at you, or do you see a person looking at right? You can see that your brain is struggling to adjust. If you look to the right side of the image, just look at the right border of the image, you will see a person looking to the right. If you look to the left border of the image, you will see a person looking at you. And this just proves that what our brain is looking for when you see things is features. Depending on the features that it sees, depending on the features that you process, you categorize things in a certain ways. So when you look to the right side of the image, you see a certain features of a person looking at the right because they are closer to your center of focus, and therefore your brain classifies it as a person looking at the right. When you look to the left side of the image, you see more features of a person looking at you, and therefore your brain classifies it as such. The point to be made here is that your brain classifies objects in an image based on the features that it detects first. So, how do convolutional neural networks actually operate? The first thing you need to know here is the elements that are included in the operation. The input image, the convolutional neural network, output label. These elements interact in the following manner. The input image goes through the CNN and then we can see an output label. After a neural network has been trained up on a certain images, on a certain classified images or a categorized the images that have been categorized prior, after that you can give it. Let's say a neural network has been trained up to recognize facial expressions, emotions. You can give it to a face of a smiling person and it will tell you that the person is happy, and you give it a face of a person that's frowning. It will tell you that the person is sad. It can recognize these emotions. And in both cases, it will give you a probability. It won't say with 100% that a person is happy or is sad. It will be a 99 or a 98% or maybe 80% when it is unclear of what's going on. It all goes down to features because that's how we process visual informations. The steps that go into this process are broken down as follows. Step 1, convolution. Step 2, max pooling. Step 3, flattening. Step 4, full connection. Here are the three elements that enter into the convolution operation: input image, feature detector, and the feature map. You can think of feature detector as a window consisting of 9 3x3 cells. Here is what you do with it. You place it over the input image beginning from top left corner with the borders you see demarcated above. And then you count the number of cells in which the feature detector matches the input image. The number of matching cells is then inserted at the top left cell of the feature map. You then move the feature detector one cell to the right and do the same thing. Since we are moving the feature detector one cell at a time, that would be called a stride of one pixel. What you will find in this example is that the feature detector's middle left cell with the number 1 inside it matches the cell that is standing over inside the input image. That's the only matching cell, and so you write 1 in the next cell in the feature map, and so on and so forth. After you have gone through the whole first row, you can then move it over the next row and go through the same process. Feature detector can also be referred to as a kernel or a filter. A feature map is also known as activation map, and both terms are also interchangeable. In a feature detector, we lose some of the information. The feature map that we end up with has a fewer cells and therefore less information than the original input image. However, the very purpose of the feature detector is to sift through the information in the input image and filter the parts that are integral to it and exclude the rest. Convolutional neural networks develop multiple feature detectors and use them to develop several feature maps, which are referred to as convolutional layers. Through training, the network determines what features it finds important in order for it to be able to scan images and categorize them more accurately. Based on that, it develops its feature detectors. In many cases, the features considered by the network will be unnoticeable to the human eye, which is exactly why convolutional neural networks are so amazingly useful. With enough training, they can go light years ahead of us in terms of image processing. Step 1b, the rectifier linear unit. The rectifier linear unit or a ReLU is not a separate component of the convolutional neural networks process. The purpose of applying the rectifier function is to increase the non-linearity in our images. The reason we want to do is that images are naturally non-linear. When you look at any image, you will find it contains a lot of non-linear features. Example, the transition between the pixels, the borders, the colors, etc. The rectifier serves to break up the linearity even further in order to make up for the linearity that we might impose an image when we put it through the convolution operation. Step 2. Max pooling. A pooling layer is another building block of a CNN. Its function is to progressively reduce the spatial size of the representation to reduce the amount of parameters and the computation in the network. Pooling layer operates on each feature map independently. Types of pooling. There are three types of pooling: mean pooling, max pooling, and sum pooling. Our main focus here will be the max pooling. See, the cheetah image is presented in the different ways. It's normal in its first version, rotated in the second, and horizontally squashed in the third. The purpose of max pooling is enabling the convolutional neural networks to detect the cheetah when presented with the image in any manner. Max pooling is concerned with teaching your convolutional neural network to recognize that despite all these differences that we mentioned, they are all images of cheetah. In order to do that, the network needs to acquire a property that is known as spatial variance. This property makes the network capable of detecting the object in the image without being confused by the differences in that image's textures, the distances from where they are shot, their angles, or otherwise. The process of filling in a pooled feature map differs from the one we used to come up with a regular feature map. This time, you will place a 2x2 box at the top left corner and move along the row. For every 4 cells your box stands on, and you will find the maximum numerical value and insert into the pooled feature map. In this case, we have lost roughly 75% of the original information found in the feature map, since for each 4 pixels in the feature map, we ended up with only the maximum value and got rid of the other 3. These are the details that are unnecessary and without which the network can do its job more efficiently. The reason we extract the maximum value, which is actually the point from the whole pooling step, is to account for distortions. Imagine that instead of the 4 appearing in the cell 4 into 2, it is appeared in the 3 into 1. When pooling the feature, we would still end up with 4 as the maximum value from that group, and thus we would get the same result in the pooled version. This process is what provides the convolutional neural networks with the spatial variance capability. In addition to that, pooling serves to minimize the size of the images as well as the number of parameters, which in turn prevents an issue of overfitting from coming up. After finishing the previous two steps, we are supposed to have a pooled feature map by now. Step 3. Flattening. As the name of the step implies, we are literally going to flatten our pooled feature map into a column like in the image given. The reason we do this is that we are going to need to insert this data into an artificial neural network later on. As you see, we have multiplied the pooled feature maps from the previous step. What happens after flattening step is that you end up with a long vector of input data that you then pass through an artificial neural network to have it processed further. To sum up, here is what we have after we are done with each of the steps that we have covered up till now. The input image, the starting point, the convolutional layer, the convolution operation we have performed, the pooling layer where we have done max pooling, and input layer from the artificial neural network, that is flattening. Step 4. Full connection. We have 3 layers in the full connection step: the input layer, the fully connected layer, and the output layer. As we have seen in the previous step, the input layer contains the vector of data that was created in the flattening step. The features that we distilled throughout the previous steps are encoded in this vector. At this point, they are already sufficient for a fair degree of accuracy in recognizing the classes. The role of artificial neural network is to take this data and combine the features into a wider variety of attributes that make the convolutional neural network more capable of classifying images, which is the whole purpose from creating a convolutional neural network. This full connection process practically works as follows. The neurons in the fully connected layer detects a certain feature. It preserves its value. It communicates this value to both the leaf and the not leaf classes. Both classes check out the feature and decide whether it's relevant to them or not. The next step becomes putting our network's efficiency to the test. Say we give it an image of a leaf. The leaf and the non-leaf classes at the end of the CNN have absolutely no clue of the image. All they have is what is given to them to the previous layer through the synapses. By now, each of these classes has 3 attributes that it's focusing its attention on: the previous layer on which this feature it detects, and based on that information, both classes calculate their probabilities, and that is how the predictions are produced. As you see, the leaf image was predicted to fall into the leaf class by a probability of 0.95, and other 0.05 was placed on the non-leaf class. Think of it this way. This process is a vote among the neurons on which of the classes the image will be attributed to. The class that gets the majority of the votes win. As you see and should probably remember from the previous slides, the process goes as follows. We start off with an input image. We apply filters or feature maps to the image, which gives us a convolutional layer. We then break up the linearity of the image using the rectifier function. The image becomes ready for the pooling step. The purpose of pooling is to provide convolutional neural network with the faculty of spatial invariance. After we are done with the pooling, we end up with the pooled feature map. We then flatten our pooled feature map before inserting into an artificial neural network. Throughout this entire process, the network's building blocks like the weights and the feature maps are trained and repeatedly altered in order for the network to reach the optimal performance that will make it able to classify image and objects as accurately as possible. This is all about CNN. Thanks for watching.